Hello everyone, this is repair time again, and here we will look at Keithley 2002 8.5 digit multimeter. This meter is 23 years old and I already had some troubleshooting done before making this video, so here you have it all disassembled. So we'll start from here and look at details and document the repairs. Model 2002 is a unique instrument because it's the only 8.5 digit multimeter in this small form factor compared to traditional full-size rack mount units. Here I also bought all the replacement capacitors required for power supply fixes, and also additional fan because the original fan is not working. PCB in this unit is not damaged from leaking capacitors, so we're lucky for that, and the replacement for the new capacitors would be rather a preventive maintenance to ensure good life of this instrument. Power supply issue is a common problem with these old Keithley 2001 and 2002 multimeters. All of these capacitors are Nichicon VX series, so they are actually decent capacitors, just not designed to run in these hot conditions for many years. As a result, all these capacitors would need to be replaced if the instrument is old and already have stressed parts. And here are some graphic images of my other Keithley 2002 that I have repaired a while back with corrosion and tasty salts on all circuitry around leaked capacitors. Only solution in these cases is removal of all components, thorough cleaning of the PCB, repair of all broken traces and interconnect wires, and only then populating with good new components to restore the functionality of the power supply. And also because the power supply is quite high voltage, there could be some more damaged components next to it, so be sure to check all of those too. So this was the unit number 2 that I repaired back in 2018. Let's go back to our current unit and we'll get introduction on analog board circuitry. So we have a pre-regulator and a tap switcher for transformer windings. Depends on what voltage you have applied at the input. So it's either 110 or 200 something volts. That will detect what the voltage is and then commutate the transformer taps through this coil. And then transformer sits right over here and provides analog power supply to this connector, and also provides the other connector goes to the digital board under the instrument. Floating bipolar supply with these capacitors actually tracking applied input signal from front-end amplifier and ensures high impedance and low leakage at DMM's voltage input. That part of the circuitry is using 470 microfarad 63 volt capacitors here and clever JFET with a few op amps circuitry there. Next we have digital opto-isolation interface. Data from CPU goes to Altera CPLD on ADC module, normally placed on a header here. Right under ADC modules is the primary DC voltage reference of the instrument, which is a good old friend linear LTZ1000A. Unlike the 3458A A9 board, this reference is not mistreated and not cooking at 95 degrees. LT1043 flying capacitor blocks also generate few other reference voltages from this 7V primary reference. Next we go to the current source for resistance function. So we have fancy VHP foil resistors that ensure very good stability and low temperature coefficient, as well as the current shunts for all the current ranges of the instrument. Some protection circuitry around them. Big white component is a high voltage divider made by KEDAC. Input protection circuits and front-rear multiple switch are responsible for input routing. Next we go to the AC domain, which is located on the back part of the board. So all that stuff is responsible for AC voltage and AC current functionality. And quite a lot of shift registers and comparators are responsible for routing all the digital signals for multiplexers, switches, and so forth. We have also on the rear the fuse for rear inputs, as well as BNC connectors for trigger in, trigger out. Both of the ADC board and analog board are 4-layer PCBs with a little bit convoluted layout because of the tight placement of all the parts required to make 8.5-digit functions work and be integrated into a single board. Let's have a look on ADC module. This is a multi-slope ADC as expected for such high-resolution instrument. There's an oscillator and current steering circuitry is over here, as well as some op-amps, zero crossing comparator, and some digital logic to control all the functions and ranges and switches. So this is essentially also acts as a brains of analog. So in the digital interface going through this ribbon cable, going through the optos, going to the ADC to this chip, and then this chip controls everything else on this board. So that's about it, and I can show you on the back. We have just passive components, nothing super fancy there. So there is about that. And there is interesting, like this is seal pad. It's actually quite thick and it's glue in place because they wanted to keep the temperature around this area quite constant. Obviously cap for the LTZ reference and just a bunch of resistors and capacitors everywhere on the board. So we'll be replacing all these caps right there, and then making sure everything works as expected. So there is no damage to this circuit board. I can show you in a good detail. So all this section usually get destroyed in case of the bad meter. Here everything looks good, so that's a good sign, and we can just replace the caps. We need to desolder all these capacitors and replace with brand new ones to ensure long and happy life of this instrument. Also, I see some discoloration down there around the 3-pin component, but probably that is fine. Some regulator or additional transistor right there. Yeah, it's a regulator, it's U108, I believe. And here is the fan that actually doesn't quite work. It's turning fine so it's not that bad, but it doesn't run, so bought a new fan. It's a Sunon. Fan is actually quite critical component of this instrument because of the small size. All the power supply components require active cooling, otherwise everything will just overheat. Removal of the fan is straightforward, just remove 2 nuts and then fan comes right off. It's connected via the cable to the digital board on the bottom of the instrument chassis. So if we check the spec of the fan, so it says here we need 12 volts, 100 milliamps. Let's see if there is any instrument in the lab nearby that we can use to test the fan. I think other repaired Keithley will be just a perfect fit, which is Keithley 2400. And I use triaxial output cable that goes into highly advanced adapter. So let's see the connection to the fan. So all I need to do is just have the positive and negative and then connect it right like so. And now we can run the fan and see what's going on. So I'll give exactly 100 milliamps and you can see what it will do. So let's turn on the output. And we are drawing 100 milliamps, but around only 6 volts. And the fan is barely working. So not good. That will cook all the magic ppms and cause the major destruction over the time in the instrument. And here we have brand new replacement fan from Sunon. So here are the specs of the new fan. I've acquired this off-the-shelf fan from DigiKey and it's matching the original fan spec pretty closely. It is 12 volt fan, around 1 watt, with noise level around 31.4 dBA. But we have different cables. Obviously, here we have the tachometer output, and here we have just DC plus and minus. So what I'll need to do is take this cable and put into that fan. So instead of doing some bodges outside, I have a more interesting idea. So we can do, there is access to the solder joint for the wires, as you can see under the label. There is no access in here. So I can destroy this fan and actually reuse this wire, put into that fan, and then it will look pretty much like original Keithley fan. And since I don't care about this dead fan anymore, all I can do is to just destroy it. First we cut the motor out for easier access to the wire, and then we can gain the access for soldering joints to safely remove the wire cable. Sure, we could add some more oil to old fan and make it work again, but we are talking here about rare and expensive instrument, so I don't want to worry about taking unnecessary risks with old cheap fan inside of the unit. Here I picked the suitable soldering iron tip, so we can get access to the small area where the wire is mounted. We'll have to relocate slightly to near the fume extractor. This section is not very exciting, so I accelerated it quite a bit to save some time. And I'm just applying some flux, removing the wires from original motor hub, and doing the same with the new fan. Just need to pull the sticker a little bit to gain access, and to remove all 3 wires, connect the other 2, and off she goes. Good idea not to add too much liquid or flux into the hub motor, otherwise it could leak into the motor bearings and cause more problems than solutions. Otherwise it's very straightforward and can be done on many types of fans, not just this small 40 millimeter one. And job pretty much done. And here we have a happy fan that is working normally with a new cable. New fan is happy and taking about 65 milliamps from the same 12 volt source. To get instrument noise a tiny bit quieter, I've added paper spacers between fan body and the frame. Also, during normal operation, voltage supplied to fan is not 12 volts but actually lower, further reducing noise compared to the full nominal 100% operation per fan specifications. It is easier to install the fan if you remove the filter holder that is mesh with the metal bracket around the back. So I'll do that in a second after a failed attempt of add all the nuts and screws without removing filter. It's just held by 2 clips on the side, so just pry it with the screwdriver and it goes right off. Just like with any instruments with active airflow and fans, you would want to make sure that filter stays clean and not clogged with dust, otherwise that would cause elevated temperatures and failed calibration of the instrument, since all of these 8.5 digit multimeters are quite sensitive to temperature and you don't need much to get out of the very tight specification margins. It's also important not to over tighten nuts, otherwise they can crack the plastic frame of the cooler, and that would be a replacement for the fan again. After the fan is installed back in, make sure it still turns freely and add the filter back. At this point we are done with the fan repair and can continue. Now that the easy part is done, let's go back to replacing capacitors. I've bought all the capacitors in the same order from DigiKey, and I'll give the link for the BOM right here. I always pick similar specification capacitors from top-tier vendors such as Rubicon, Nichicon, or CDE, AVX, or Kemet. Very same capacitors are also used in Keithley 2001, so if you repair in that one, you can use the same capacitor list and procedure is exactly the same. And then the temperature I use for desoldering is just gentle 270 degrees. You don't want high temperature. Now a few words about desoldering. Good soldering technique require adequate thermal contact to spread heat in the joint evenly. This is why experienced engineers often add new solder to the joint even if they are removing the component out of the board. This helps with wetting and reduce heating time for smaller thermal stress to component. It is helpful to use largest tip available that can fit into the area where you are soldering to bring more heat capacity and reduce cooling effect from the PCB copper planes and nearby components. Remember, solder melting point is just 210 or 230 degrees, so it's not the high temperature that you need for good repairs, but a good thermal conductivity. Hopefully this information can help beginners who increase temperatures to some crazy above 300 degrees centigrade when components do not want to desolder well, and mostly that is because small fine tips used or underpowered compact soldering irons like battery powered irons and stuff like that. And here I am showing another method to remove through-hole components like capacitors by heating both pins in quick alternating way. I could use wider tip here, but then it would cause PCB heat too much, especially for fragile 4-layer board like this Keithley 2002 analog board. It may cause delamination and a damage to layers inside of the board. Not good. Heating each joint separately introduces less heat to the board, so I'm doing this for all the capacitors removal. You need to be quick enough so the added heat to each joint is building up until the liquid point is reached on both of them. Once that happens, capacitor comes right off the board with very gentle pull. Be patient and do not try to pull capacitor by force, since that will overstress PCB pad and often rip the inner copper connections. So it's not a very beginner friendly way, but it's working pretty well if you are experienced and already practice on less special boards. What we will need to do now is to free up the space. And for that I will use good old toothpick method that I shown in a previous HP3458A repair saga. We'll continue to that instrument in some not far away future, but for now let's focus on this 2002. This is quite boring, so I skip this part and do it off the video, and we'll continue when it's time to replace new caps. Here I am placing all new parts into a board while checking correct orientation and polarity on from reference photograph of 2002 from previous xdevs.com repair article. Repairs like this are one of the reasons why I always encourage people to take photos and share them publicly online, so the next person after us can save poor instruments from landfill and polluting environment. My dream and wish for today product manufacturers is to think about servicing their equipment not today or perhaps not next year, but 10 or 20 years from now. So providing service information required for basic repairs like I show in this video. This would be beneficial for both manufacturers and loyal customers who would continue to use their products and promote good instruments years to come. Having zero service information like we see in today's wasteful consumer market should not be acceptable for professional test equipment market, especially considering the cost of modern equipment. We should not accept throwing away thousands of man-hours and expensive raw materials in broken equipment just because some $5 fan failed and caused a capacitor in power supply to blow up. I recognize that there are intellectual property protection issues and safety reasons for not providing service information, But even simple overall board layout photographs, cabling and block diagram in service manual with BOM list would make wonders for repair industry. After all, today's equipment is so complex with high level of integration that copying or duplicating design from a few photographs and a BOM list isn't just doable anymore. And here we have finished with all the caps replacement, so we can reassemble the Keithley 2002 back together. This is pretty straightforward, so I will just speed up this part on the video, and we will see if the instrument is functional again and do some tests. Interesting that seal pad is matching that orange tab on the cover. Because of the small size, it have to go in a specific angle, so it's a little bit tedious, but quite doable after you do it for a few times.
And that slides out.
All this is not very interesting, so I'm sure many of us already saw how to assemble Keithley 2001, and the process is pretty much the same in Keithley 2002. There is a specific order that you need to assemble the things back together, but other than that, it's pretty much straightforward. So we have the board in, then install the transformer, add all the connection terminals, and plug the cables back in. Put the front filter in, and rest would be installing the cover and getting the rear filter in. And that's pretty much all it is to reassembling 2002. And of course, sometimes we have left with the spare quote mark unnecessary components because I forgot something to install in the proper order. Like in this case, it was front rear terminal switch plastic rod that toggles the switch on the main board. So I'll show you how I realized that and reinstall it back by lifting the front common mode choke. Here it is. So it took me about a couple minutes to get everything done. Once that is sorted out, we can put back a black conductive cover in, and then proceed with securing the rear BNC connectors and essentially getting meter ready to first power on. For first power on, I will use Chroma AC source model 61604, so we can check the consumption and make sure everything looks normal. So here's the AC source. It's programmable from 0 volts to around 300 volts, and here I just programmed it to 120 volts 60 hertz output.
And I forgot obviously the power button, so we will need to actually install this thing. So give me a second. Always forget something. Alright, now we're ready to go. Let's power on. Fan is okay, and we are booted, and we get first we can run the self-test. So let's do that. Built-in test, automatic, full, continuous repeat. Remove all inputs. We have button off. No problem so far. Running the full self-test.
This runs pretty quick, so not much waiting here to do. And after this, it would ask to short circuit high terminal to the amps white jack. So we can do that with the external cable. Doesn't matter what cable it is, it's just for the self-test, margins are quite wide. And then the next step is 4-wire short to check for resistance for wire functionality. All self-test is completed, and it's a good sign. If there would be any errors, there would be a star next to a complete word. And just to be sure, we can restart the test and run it again after some time. Some of the leakage issues can be just random, so not always present. So it's important to run the test multiple times.
Self-test pass, calibration short, destroyed.
No repair should be done without sacrifice. Now we are done with hardware repairs and completed self-diagnostics. It does not, however, mean that instrument is fully working and meeting Keithley factory specifications. No repair is finished until the calibration is fully completed and results are verified with known uncertainty. This task is a longer one and will be done in future as I continue to use this meter and run it through all the functions and ranges with my Hulk Fluke 5720A multifunction calibrator steam. More details about similar process are available in earlier January video where adjustments and calibration on different unit of Keithley Model 2002 8.5 digit multimeter were presented. On this DMM I've completed only one quick automated 16-hour test, and I'll show you some of the results in this video. And this instrument is taking about 30 watts of power according to my AC source. So I'll leave it running 24/7 so we can monitor any drift or instability or noise issues over some weeks of time. And here is the glimpse of internal XDEV's software that running different calibration points and steps to generate a report, so I don't have to sit in front of the meter and press the buttons and mangle with cables all day long. So I can do other things like a full-time day job and things like that. I've been developing this software internally since 2016, and it supports a variety of different instruments, including Keithley 2001, 2002, HP 3458A, and so on. And here we have a first result. So this is all DC voltage functions, and we can see this meter is light up like a Christmas tree with all the red fails. And this is not unexpected because it was last adjusted and calibrated good 20 years ago. So the similar situation is on resistance ranges with actually few ranges passing in 24-hour specs, but most of the others fail. And zero short is actually quite okay, so no problems with the front rear switch. That's a good sign. And AC voltage is actually all good because of quite loose tolerance for Keithley 2002. So it's not that particularly demanding test, and all the ranges and all the frequencies seem to be well inside of the margin for 90-day spec. And the similar goes to the higher voltages like 20 volt, 200 volt and 700 volt. So no problems with ACV. So we don't have to repair any of those circuits, which are quite elaborate. So that's also a good sign. And in quick test, I didn't test for DC current, but I did test AC current, which is also good. And the worst deviation is around 45% for 10 kilohertz. So that's it for now, and as always, thank you for watching, and be sure to check xdevs.com for repairs of Keithley instruments and many others. And if you have any questions about this or other repairs, feel free to reach out using xdevs.com contact information.